Thank you, Nuno, for the invitation. The objective of this training session is to to show you what you can do and what was the incentive of this using Docker to package and bundle stuff for teaching related to MD, but also actually research. And the whole idea will be to go through an example and then we're going to build something together. Unfortunately, I will have real trouble to monitor the chat and while doing the demo, so feel free to interrupt me and ask questions. We're not that many people, so we can make it like way more interactive than usual by asking questions and comments during the presentation, right? Okay, I take it for yes. So my name is Sebastien. I'm working at McMaster University since January. Before that, I was working at UQAM and then Université Côte d'Azur. The common point with all the different things and the different labs where I've worked in is that we were always trying to release software in a way, and we're also quite heavily invested in teaching. So the presentation and the things we're going to do together today, it's really related to kind of this expertise that we develop. It's me talking, but it's working with a lot of different people actually, related to how you can package and release software related to MDE. And I will try to go for the beginning of the presentation into things that are like example of good way of doing stuff. And at the end of the presentation, we'll go more into the dons, so the lessons learned, because we started working with Docker and containers in 2014. Actually, it was really new at that time. So we have some like things to share with you guys today about that. So the main problem and why I'm talking here today was a discussion with Stefan eons ago, actually, who was aware of the work I was doing with model-driven engineering in an Internet of Things context. And it's kind of a nice lab that you can work on top of Arduino microcontroller platform. And Stefan was like, oh yeah, that's just, what you're doing is pretty cool. Can you package it as a learning resource for the MDE network? That was quite cool and a very nice request. So offshore, I've accepted. And here's some blatant advertisement. If you want to go to the learning resources in the MDE platform, community platform, you can go and check this this learning resource, which is, in my opinion, very cool. But I was quite afraid of doing this when Stefan asked me, basically because, well, IoT implies hardware at some point, and making stuff related to hardware available to a global audience in a non-controlled way, because when you're teaching it like in a lab or at the university or in a tutorial, you can kind of control the environment, but this would have been reliving things in the wild. So I was really afraid of the hardware part. And the point was like, well, we'll figure it out. So actually we did. And it was quite easy. Like on the left, you have the real setup with all the wires and the microcontrollers and the light, the 7-segment counter, the button, and all the things we, as a student, to do with this. The learning resource is about building different languages at different level of abstraction to program these beasts. And actually making this available for the MDE network was super easy. We took a simulator, which is called SimulIDE. We built a breadboard and the microcontroller with this. That was actually way simpler than by using the real wires, because you can't burn anything and you can't destroy any light or any 7-segment counter by using the wrong voltage or stuff like this. So it went really well, like extremely well, actually. But surprisingly, what took me the most amount of time, like it was really, really long, was to find a way to package the compiling toolchain, because The whole learning resource and the whole idea of this lab session is to build different languages to program the microcontroller, but it's a code generation approach. So eventually you will generate code like this, which is basically C code linked to the Arduino standard library and the AVR stuff. And then you have to compile it to go to like binary code, and then this binary code needs to be loaded to the microcontroller, the physical one or the simulated one. And surprisingly, it was this transformation from like this compilation toolchain that was extremely complicated to package. Why? Well, basically because it is using non-trivial software that works quite well on Linux, a little bit less well on the Mac, and terribly wrongly on a Windows platform. Then you have some local setup that are linked to where your version of the Arduino microcontroller description is available on the local computer. So if you have two students that install it in different way, then you will have subtle differences between those paths, and then it can be a nightmare to debug. So what was kind of totally okay in like in a local setup when you're controlling the computers, like in a lab hosted by the universities, that was quite easy because it was like replicating a given image. But in the context of a remote teaching and autonomous and asynchronous remote teaching, like providing the learning resource and having someone playing with it at any time, it would have been a huge nightmare to let it like in the wild like this. So basically, the idea was to use containers. Containers, in a nutshell, it's a way to bundle stuff into an image. Then we can upload such an image to a shared hub, which is, in the case of Docker, called the Docker Hub. And based on this, people can download the image and instantiate it into containers, and then you can use the containers that bundles and package all the complicated tools that you need to have inside the container. So instead of having to install different things onto different computers with different stacks and different people doing it, you just build it once, like package it once, and the only prerequisite on all the other computer would be to have a Docker engine available, which sounds pretty cool. So what we're going through today is basically 3 steps. First, we're going to bundle a command line interface into a container. Then we're going to add a graphical user interface like an IDE and some persistence so that students can make changes, and then the changes are persistent on their computer. And then we'll discuss some lessons learned about how we used it and in different contexts, not only this one, and how it can be useful or not at different points. Any questions so far? Okay, so let's go for the first part. First, what is your confidence with? I will try to get the training session. Can you like react inside Teams with your level of confidence with Docker? Are you quite confident about it, or I mean, you know it, you. Okay, so various audience. That's cool. That's cool. Really feel free to interrupt. I will try to like be very gentle and simple in the concept, but trying to emphasize what's important in those different steps. And that's it. There's no way to just see the chat. Okay. So First things first, what we need to have is what's called a Docker file. The idea of a Docker file is basically a text file that will describe what we're going to put inside our image, thus inside our containers, all the software stack. We're model-driven engineering guys, so we would have liked and loved to have a model here, but unfortunately, it's really not defined as a model, like in a descriptive way. It's defined as an imperative programming language, kind of. So basically, you have what's available on the left, on the right, sorry, that the getting started tutorial from Docker, where you basically have one important thing, which is this line. This line is the from, because Docker uses a compositional model, so you're always composing your image with a previous one. And then you can recurse to the root image, which is called scratch, which is basically the empty hard drive. But then you can reuse what was already defined. So in our case, if you want to bundle something that is on top of Java, you can use an image that already contains Java installed. If you, in this case, have something related to Node.js and you want to deploy something on top of Node.js, then you just use this version. And then, now that you have your image, like your basic canvas to start painting the picture, so bundling your application, you can run some commands. And those commands like run, workdir, copy, CMD, expose, and kind of things that can be quite trivial or quite complicated. But the basic point is that you're describing in the Docker file what you're asking Docker to do to create the image. So how the different software that you want to bundle inside your system are packaged together. So we're going to build a very first Docker image together. So we're going to do something quite simple related to the MD in IoT context stuff that I was describing. So what we're going to do is to create a Docker file that contains those information. It says we're starting from a version of Ubuntu called Focal, which is like the release tag, the release name. And then inside this image, we're going to run those three commands. First, we're going to update the packaging system. Then we're going to install and always say yes if ever we are asked any question. We're going to install Makefile and all the stuff related to Arduino, like all those kind of things, Arduino Core, GTC AVR, AVR Jude, and AVR libc. So with this, we're going to have a description of the command line interface tag I wanted to have inside my system. So we can do it together. I will just try to get this. So I have this Docker file prepared in a way. Let me check. Why it's not zooming? It's zooming. So we have the Docker file, which is named Dockerfile, saying from Ubuntu Focal, run those commands. And then we can basically, so I can put it in the chat if you want to do it. So that can be quite long if you're doing it on your own because it requires to download stuff, but yeah, the Docker file is a really leaky DSL. That's for sure. And then this is a description. So now I need to build the associated image. So let's build the image, and to build it, I'm going to ask Docker to do it for me. So I will basically ask Docker to build the current Docker file for the current directory. That's why there's a dot here. And we're going to give it a name, and the name will be Ace Design, which is the name of my organization on Docker Hub. And we're going to call it MDENet. So basically, Docker is doing things. It basically required the Ubuntu things, and fortunately I've prepared a demo, so I already had Ubuntu on my computer. If not, it would have been quite long to download it. And then it basically run those commands, and it's export the image into something which is called Dockerizing, AceDesign, MDENet. So now that I do have the image, we can try to like run it, because for example, I have this here. This is my main.c element. So this is the code, the C code that I was showing you last time. And so this is my C code, and I want to compile it. But you see, I don't have the AVR and I don't have all the stuff on my computer because it's not installed in the host. So if I try to AVR gcc main.c, it says, well, command not found. I have absolutely no idea what you're asking me to do. But now that I do have my container, I can basically run it. And to run it, it's also quite simple. Now that it's built, I'm basically asking Docker to run and remove the container when we're going to stop it. If not, you will accumulate like zombie container. I want to run it and remove it when it's dead in an interactive mode using bash as my entry point, like as my shell. And I'm going to start the image we've just built previously. So by doing this, well, you see that now I'm root inside the container. I'm no longer my user on my local computer. And then I can start to use AVR GCC. That AVR GCC exists inside the container. Of course, I don't have access to any of my files because I am inside the container. So I'm kind of now isolated from the host, which is good in a way because I can put everything in the stack, like very complex software. Imagine if you had to work with Python, you can nicely package the right way the different things you want to have inside the image, and then you can run it. But one of the main issues to date is that we don't have a way to share a file with the host. We're going to see that in a couple of minutes. But now I'm inside the container, and if I want to exit, then I'm going to exit the container, and that's it. I'm now back on my local computer where AVR GCC doesn't exist. Something really important is that the containers are transient. So if you're modifying the container, like you're adding file, you're making some modification at runtime during its execution, then if you stop it, you will lose those things. So it's really about building the image with all the things that needs to be there, and then it's kind of a sandbox where you can do everything you want, then you stop it, and everything's like reverted in a way. And now, last step, that what could be cool in a way is to be able to share this stack with the students or other fellow researcher. So to do this, I will basically push my image that I've just built into the Docker hub. So I will basically ask Docker to do this for me. And then it's pushing the things to the hub, and we can go to the Docker hub. And we can go to the organization, and then there's the test that I was doing last night, and because it's still uploading, but we'll see that now it's going to end uploading in a couple of minutes. And it means that now any one of you can use the AceDesign/MDENet image if you want to actually run this on your local computer with Docker. It would just require to, let me just put it in the chat. Okay, there's a lot of things happening in the chat, so I don't know if it's. I really can't see the chat while talking because I only have one screen. So if you really do have questions, just please interrupt because that will be way easier.
I think it's just been a side channel conversation there.
Yeah, it's a bit of a chat that we've had.
Some of the fun that you can have with Docker, if fun is the right word. There was one, I think there was one question from Antonio before about whether you actually need the entry point argument. I suggested that you do because you haven't defined one in your Docker file yet, but
that's it.
I'm not sure whether that's correct, so you might want to correct me on that.
I think by default you get a default shell, which tends to be bash in the case of Ubuntu. Anyway.
Yeah, that was yours spoiling my plot twist.
Oops, sorry.
No, but we can discuss it right now. Actually, the as I was saying here, Docker is a compositional system. So you're always building something on top of something else, and then you're inheriting, in a way, all the assumptions that were made in the previous image, the image you're extending in a way. So if you don't specify the entry point, then you will fall back on the entry point that was defined by the previous people. But then this is a fragile assumption in a way, because at some point you're using the Ubuntu version, and then it's bash, so you can use custom bash commands because, well, you know, it's you're working with bash. But then at some point you switch to another one to reduce the size of the image, or Ubuntu make another decision and switch to another entry point, and suddenly you're not using bash, but you're using ZSH, or you're using TCSH or any other, or basically just SH, which is way limited with respect to bash, and then suddenly nothing works in your thing because you're assuming that something was like available by default, and actually it wasn't. It was just like here by accident in a way. So that's why it's kind of a good practice to specify the things that you want to have at the moment you have it. That's also one of the problem with the fact that it's imperative and you're always scripting and you're not really declaring what you want and what you need inside your image. So this was what I was saying. On the host, no AVR. Inside the system, AVR but no file, and then back to the host. So now that we have this idea of we have stuff inside the host on the host, sorry, and we have stuff inside the container, we can basically start loading stuff inside the image to make it available for the container. So we're basically going to add those two instructions. The first one, the work dir, is to say, okay, let's create a directory that will be our current directory, and that's going to be where we are going to work. And then we're going to copy from the host the main.c program into the image. So it's quite simple. We're basically taking this, and we don't need this anymore. And we're going to take the Docker file, and we're going to add those things. And then we're going to ask Docker to build it again. So we're building again. There's some caching mechanism that do exist, so we're not recomputing the image at each time. The lines that were not touched will not be recomputed. If I'm adding something here, then it will rerun this image, this instruction, sorry. But if I don't, then it considers that the layer is done and that there's no need to redo it at any point. And then it basically created those two things. So now I can go, I can run the image. And you see that before I was in slash, but now I'm in /demo because I said that this is my work dir. And if I go here, I have the main.c, so I can basically use AVR GCC to do this. It's not really convenient to have this like only the main.c, because it's quite complicated. We have to combine the AVR GCC and the AVR OBJ copy thing. So what I'm going to do is basically to also copy my makefile inside the system. So this is Arduino makefile, and we're going to call it makefile. Let's rebuild. Let's restart. And then now I have the makefile and the main, so I can run make, and it worked pretty well. Everything was executed, and now I do have my makefile, the C code, and all the different artifacts that needs to be uploaded into the microcontroller that are available here. So that was, again, pretty cool, but main issue is that if I exit the container, then I've lost everything, because everything that we've done was done inside the container and not on the host system. So that was adding the makefile and executing it. And now if we want to really turn it into a turnkey image, that was our entry points discussion, instead of providing the entry points /bin/bash at each time, we can really provide it once and for all by providing this in the Docker file. So with this, I basically have bundled what I wanted to bundle: my compilation toolchain that goes from C code to let's say Arduino microcontroller binary code, and I've put inside the image some elements and the makefile to compile those elements, and now it's turnkey. So if we go back, build again, and if we run it, now we just have to run this. So basically what I'm asking is Docker run remove when dead in an interactive mode the image I've just built. And then basically you can make it works. So all the things that were daunting at the beginning about how to package those things and make sure that they were available was actually quite not such a big deal by putting everything into the image. So if we take a step back about what's happened, we've just it's 9:30, so it took us 15 minutes. We've bundled a non-trivial stack into an image. Actually, the real complete stack for this learning resource also contains Lustre, Java, Maven, and other stuff. So that's kind of way easier to provide an image and tell to the students or the fellow researcher, just run this command instead of install this, install that, do this, do that. That could be quite annoying. We shared the image on a public repository. So, oh yeah, I forgot to push again. And you see what happened? It's when I pushed, it used the layer cache mechanism. So it considered that those two layers already exist in the hub. So it only pushed the new addition that I've made. So basically the work dir, the entry points, and the files that I've had. So that's a way to minimize bandwidth in a way, because you're actually exchanging layers that are stacked on top of each other, and you're not really exchanging a whole and complete image. And finally, which is really cool, is that you only need the Docker engine to run the software. So that's pretty neat, actually. Limitation to date, well, we can't really use this in a teaching context because there is no persistence. So the students would work with the stuff and then lose everything for any reason, like typing exit in their terminal. So just not really working. And we also don't have any IDE, which could be a problem if we consider something related to modeling, domain-specific languages, and those kind of things. We want to have those nice way of supporting the developer while using the languages. So that was quite a problem because the learning resource was really about having 8 different languages defined on top of those microcontroller code to raise the level of abstraction. So if I can't provide any way of editing the code and any way of the students to have a persistent lab work, then it's not efficient. So basically, second step will be about bundling a graphical user interface and adding some persistence inside the system. So first, we're going to dig into the persistence, and we're going to use what's called volumes to do that. The point is to have an access to the host file system. So as we said, containerized, isolated. So that's really good because then you can do whatever you want. It's considered as a sandbox, but it's also not good because then when you terminate it, then you've lost what you're done. But those are also Linux system. Actually, it's LXC subsystems. And in those kind of environments, you can basically access disk storage with what's called mount points. So that's the very same idea. We're going to mount the local file system inside the container so that we're kind of breaking the membrane that do exist between the host and the container, and we're going to have communication that will exist between those two. So to do this, instead of what we were doing before, which was comparing stuff inside the container, like the C code and the makefile, we're basically going to say, hey, no, we're not going to do that. We have a volume named Gmo, and that's where we're going to work. And that's it. So we're basically declaring like a dandling directory inside the image. So let's do this. So instead of doing this, so let's we're going to say, here's my nice volume name /gmo, and here is my this is my working directory. And we're going to build as usual. And we can run. So I'm in Gmo, but basically, like, there's nothing inside Gmo because this is just like an entry point to like bind this directory to my local host. So if I want to really have access, I need to that's what I was saying. I will have to use what's called volume mounting. So I will basically mount using -v for -volume, for example, my current directory to /gmo inside the container. So it's local directory, colon, where you want to bind it inside the host, inside the container, sorry. So let's do that. I will bind and now I do have access inside the container to all the things that are stored in my on my computer. So basically, if I want to compile this using what is inside the container, I just have to run make with this. So like previously, it worked. I have all those artifacts that were created, but which is interesting is that this is also happening, where is Visual Code? On my local computer. So I now have access to the different files that were created as compilation products. So I basically managed to have bundle the software stack that could be complicated for the students to install inside something, and this container now can interact with my local stuff. So now this is totally persistent because this is, well, what's happening inside on my computer. And if I here ask make to clean the mess, sorry, then it's clearly modifying what's happening here. So the stack is bundled, but the files are local, which is what I wanted to do in this.
Sorry, Sebastian, to interrupt. How do you deal when the difference between the user IDs and the group IDs between the container and your IDE? Because inside your container you have root. So if you change anything, it will show up as owned by root. But if you change things on your IDE, they will show as owned by your user.
Yeah, let me. So this is a local one. We're going to run it. So you see that in this case, what's happening is that inside the container, all the files are owned by root, but on my computer, it's owned by me because I'm the one running it. The permission model and the user ID and group ID model in Docker kind of sucks, to be honest. And it can be a mess. That's part of the lessons learned that we have. You raised a very good point because it can become a nightmare. Especially if inside the container you start to play with the users, like not running it as root, which is actually a bad idea to run everything as root on a daily basis. Then it becomes like really, really tricky to have something that is stable. And also the other problem that this behavior, like this is owned by me, is true on the Mac. I think it's true on Linux, but I'm not sure it's true on Windows-based computer right now because they've changed the way.
I was actually going to say that the behavior that I'm used to when I've used Docker is actually the other one that you said that happens in Windows. So in Docker, what the issue I have when I use volumes is if I don't do something, it will show up as root from my host system, and then I have to do all kinds of leaps and bounds to make sure that the user ID and group ID inside Docker maps to the user ID and group ID in my system. At least, maybe something in my setup, but
no, it's also Docker had the terrible habit, let's say, of changing things and semantics when changing versions, for example. So something which was true in Docker 12.8.9.a will not be true in 12.9.8.c, but then will be true again in another version. So they really have no real, let's say, value for retrocompatibility, which allow them to be like very neat and release features in a really quick way, but that can become a nightmare in terms of reproducibility. That's part of the lessons learned. Like we really had some big troubles with this, and also a way to be sure that it fits is it's like the entry point. Actually, if you don't want to rely on something which is available by default, just specify it. So that's what you were saying. You have to be sure that what's happening inside the container matches what's happening on the host, but then this is kind of breaking the idea of container isolation, because then the container needs to be customized and tailored based on the host it's running on, which makes it like a maintenance hell again. So this is part of the weaknesses of Docker. They're really fragile in the way they're handling those kind of things, and in the way it's communicating with the host. That's for sure.
So actually, this is a problem that I run into, and the way I just posted a link in the chat to the way that I normally deal with that specific problem. And rather than checking the slide that I got it from, basically says this is a problem unless you're a Mac or VirtualBox.
But then you see there's on this very version there was no problem. So it's really depending on way too many factors to.
Because you're on a Mac, that's why.
Yeah. Any other questions? Okay. So now that we do have this, we can say that okay, let's try to bundle an IDE, because that's a request that I've often receive actually. This is a real email sent from by a friend last summer. It was like, hey, I have this very nice Eclipse plugin and dependencies that is a mess to install inside Eclipse. I would like to package everything in a way that it works for Windows, Linux, and macOS, but minimally on Windows. Can we talk tomorrow? And actually, the short version and the short answer to this request is, well, I'd be happy to talk with you because it's been a while, but it's just not possible. You can't bundle Eclipse as is inside the container. While, well, basically because the container is really all about server-side stuff. It's basically a mini Linux available that was created in the at an age where starting a virtual machine was quite time-consuming. So they were looking for something that was able to start in the wing of an eye, and that was really the point. So, of course, you can, because there's a lot of way to trick the system. For example, you can use you can put an X server inside your container, and then you can use SSH tunneling to connect a local X server to the one that's running in the container. You can use remote desktop. Yeah, there's a different way to do this, but then again, you're becoming host dependent in a way, and of doing this, and it's not really the essence of the thing. So if your idea is like, okay, I have this very nice graphical user interface that works on my desktop and I want to put it inside Docker, it's just not the right way of the right way of thinking about it, because this is more a virtual machine case where you can bundle a desktop and then you will share this desktop with other as sharing the image. But if you want to share an image like a computer, a container, sorry, it's really all about kind of server-side stuff. But then we are now at an age where we do have web-based IDE. Eclipse does have a web version actually. Visual Code host he's hosted on the web and is actually a web application. So what we can do quite easily is to host our web-based IDE inside our container. Then we'll have the IDE running. It's a server, so it works quite well. We start the container, we connect to it through a web browser, and then we have access to the editing the files. So that sounds like the right way of doing it. So to do this, we're going to install Visual Code inside our container. So basically, it should be Visual Code, not Visual Studio. We're keeping the same source image. We're keeping the same Arduino stuff. And then what we're going to do is to basically go into a directory named code server. We're going to download the Debian package, because Ubuntu is based on Debian, of code server, which is the easiest way of running it. So we're going to unpackage it, install it, and then we're going to copy some configuration, like the password to connect to the Visual Code server inside our container so that it's configured. And then we're going to go back to our demo directory, because that's where the code is. And we're going to change the entry point to not use the bash system, but use the code server. So now it will be running on the demo directory. So let's do that. I've cheated a little bit, and I'm going to use the Dockerify that I've prepared yesterday, because it will be way easier. Let's take Visual Code. So that's basically what I was showing to you guys, where this didn't change. We use this CURL, downloading the stuff, running the installation, copying the configuration, and you can check that the configuration is really like, this is the port we're listening to, so this will be running on port 8080, and we need a password, and the password will be MDENet, and that's it. So now that we have this, we can build again. So we can build. And now that we've built, everything is cached on my computer because I've run it like yesterday, but if you haven't cached it, then it would download the stuff and actually install it and everything. Now that we have this, we can basically run the image. And so now, instead of starting a shell, it basically started our HTTP-based IDE. So I can go to this URL and sure. We talk about isolation of container. So the container is isolated from the host. There's one way to break this isolation at the file system level. It's using volumes, but then you need also to do it at the network level to bind a network port on my computer to a port in the inside the container. So I basically need to tell Docker that I want to kind of tunnel the port 8080 on my computer to the port 8080 on the inside the container. That I could use another numbers, but that's it. So now that we have this, now I'm connected to code server inside the container, and I will use the password, which is MDENetwork. And so things are happening inside the container, but then you can see that I have access here inside my browser to the C code that we were doing. So for the students, that's quite cool because you can bundle everything, like the IDE with the right plugins configured in the right way, with the right support. You can put the right compilation toolchain inside your container, and you can like provide it as, okay, this is a bundle, just download it, use it, work with it. You just have to know one command, which is basically this command, like this is how I want to run it, bind the current directory, bind the port, start the image, and then you have a turnkey artifacts that you can use for teaching / researching. So that's kind of cool. So based on this, now we have something cool because we have the persistence, we have the IDE, and everything is bundled in our image. I can push, so you can share it if you want. For the demo, we use Visual Code, but actually we can have used Eclipse. And there's also interesting stuff, but if you're thinking in terms of DSL, and there's those language server protocols that can be defined to provide support for language, and this can be a way to this. What I was showing today is really like, this is an easy and turnkey way of doing things. Like you can put everything in an image and then you can package it to the students. But if you want to do something with more modularity, like only exporting the support for language and making it available, then that's also possible in a way. This was just totally out of scope for the for what we're doing today, but this is they're the way to be less, let's say, gross in the way we're doing those things. Main issue now, I don't have access to my compiler toolchain anymore, because now each time I'm starting the container, which I was doing here, it starts the web server, and that's it. So I can't do run the makefile and compile the C code anymore, which is an issue, because then I've won the IDE, but I've lost the access to the toolchain. There's different way of doing this. The first is basically to use multiple containers, like bundling the IDE into one container, binding the compilation stack in another container, and asking the students to run both at the very same time, and they would share the same directory. That's a possibility. Could be a mess in terms of file permission, as we were discussing, but that's a way. It's basically the idea behind what's called Docker Compose, which is more a network/service orchestration thing. But that's really the point, that you have a lot of different containers that are independent and that are like cooperating together to achieve a purpose. The other option is to basically use simple solution, keep it simple, stupid. So we put everything inside one single image, which is the one that we're going to share with the students. And we're basically just starting the container that will start the web-based IDE, and then we're going to attach to the container, like to start something in addition to what was already started. So that's what I'm going to, yep.
Sorry to interrupt you, Sebastien. Can you just start a shell from VS Code? If you want to just run some commands in there?
That's also an option. You can you can have stuff running inside the VS Code, and you can start the. Oops, sorry. Then, oops, sorry about that. At some point, there's a way to pop up a shell somewhere. I just don't remember where.
I think it was the 3 lines at the top left, and then there's like a terminal menu or something.
Yeah, terminal, and then you can start something, and then so you can run it here. But so that is totally possible. But my point here was more to demonstrate, like, when you have to bundle different things together. That's right. For sure, if the web server gives you a way to have access to it, then it works. But if you really want to have things in the terminal and things in the like in the IDE, that's also a way to do it. So I will just quickly demonstrate how to attach a container to a container, and then we're going to go to the discussion. So basically, the idea is that we're going to run our container as a daemon. That's a service that is now available on the computer. So we're going to basically add the -d option to say, okay, that's now this is a service. It runs on itself in the background, and we're going to give him a nice name, in this case MDENet. And then each time I want to have like access to put my ends inside what's happening, or if I want to start something different inside the container, I can basically connect to the running container. So it's not starting a new container, it's really connecting to the one that already exists. And then I can basically run bash and do whatever I want to do inside the system. So let's add this. So it will be named MDENet, and it will be run as a daemon. By doing this, which is interesting, is that it stops. I don't have access to the logs anymore. It's like really going into background, so it's running. It gave me an ID, which is the Docker underlying ID for the thing. And then if I want, so if I go back to this, I do have access, so everything's working. I can add stuff here. And if I want to start my terminal, I can go with this. And now I'm inside the container. So I can touch a file. And the file do exist inside the IDE. So it's basically we have one container that is running the service, running the language server protocol, running the Eclipse web IDE, like whatever, and then you can connect to inside the container and see what's happening. So if we take a step back, we've bundled a non-trivial technological stack. In this case, it's just AVR, but in the context of the whole MG for the IoT learning resource, that was way much more. We now have an IDE embedded inside the container. The IDE gives us access to the shell, but we can also have access to the shell because we have this nice way to start everything and interact with the system. And the cost of this was basically simply having Docker engine available on the computer that will run this. And if you have this, then you can just download the image, run the image, everything is bundled, and it works like a charm for the students. So we can use like the last minutes to discuss some lessons learned based on this. So as I said, we're playing with Docker with colleagues since 2014. We used it in teaching context for an intro to software engineering course, which was an undergrad one, for a microservice architecture design course, which was a graduate one. And we also played with it in a research context, let's say, to package reproducible experiments to support various tutorials made at RE principally, and also to run some experiments at large scale, because it's a nice way to, if you run things on a computational cluster, it's a nice way to run it on an image, so you're sure that that's the same code that is executed in all the different nodes. So the most important lesson that we had, which is quite weird as a conclusion for after 1 hour of talking about Docker, would be to try to avoid using Docker when possible. Docker is actually really pretty amazing. Like it took us 25 minutes to have something up and running, and we had this stack that was nicely packaged and it works quite well. But this is kind of fake advertisement in a way, so that works well for sure, but it can become a maintenance hell because the entry ticket is super low. You have this nice DSL that looks nice, but after a while you try to realize that it's kind of leaky and flaky and not really reliable to the to something which could be stable. And in addition, the semantics changes from a version to another, so that's kind of annoying. There are some alternatives that do exist in addition to Docker. Docker is the easiest one if you just want to have something that works quite quick, quite well with something that you need in a very short-term future, then Docker is clearly the right choice to package teaching resources or research resources. But if you want something which is more stable, I'd really recommend using for Singularity or using with stuff like Kubernetes and things like this, which are, let's say, with more control in a way. Like Singularity is really good in terms of file system and those kind of things. That's actually, if you're working on HPC grid, Docker will not be available, but Singularity will be available because the Singularity knows how to handle file system. Something cool is that all those different container and image system follows the OCE, the Open Container. I don't remember what the I was for, but that's kind of a standard way of representing image and containers. So you can have an image built with Docker and executed with Singularity at runtime, for example, or the other way around. So that's a good way of using different tools to achieve your goal. Basically, when we're working on the HPC cluster with the students, we were building the images with Docker because the DSL was easier to use, and then we're executing the images with the containers with Singularity because Singularity was available on the cluster. So you can basically mix and match all those different things. And that's like when we realized it was such a mess to use Docker, we actually digged a little bit into it, and it's really a mess. Like if you really look into how people are using Dockerfile, we made this study with Ben when he was a PhD student in the group in 2018 about how people were using Docker and Dockerfile, and there's violation everywhere of the guideline. It's really easy to make some mistake because of the black box composition model. You're reusing stuff from the previous image, but you have no idea what happened in this image because you don't have access to the code that was used to build it. So basically you can reinstall software that was already installed. You can violate guideline in the way the stack is packaged and bundled, so that's it's kind of it can be a mess actually. But if you really take this as okay, I need to bundle something which could be a nightmare to install and replicate to different students' setup, and I need to have it simply package, then Docker is again the right choice. Even if we have some subtle issues with the underlying OS, we were talking about the differences between the file permission model if you have a Mac or if you're not on the Mac. There's also some interesting memory management issues, like the access to the RAM memory can be quite tricky because by default Docker will only gives you like 2 GB for your computer, but 2 gigs could be way too small if according to the images and what you've bundled. So you have to change the configuration on the host to have this. And Docker also have the very bad idea of making those very big images. Like the example we built together today weighs around 1 gig. Basically because we bundle on top of Ubuntu, and Ubuntu is quite big. So there's a way to reduce the size, but that's quite usual when you're working with Docker. You need to take care of the size of the images you're building. So really to just give some example of why the size can be an issue. I'm a PC member of XE Artifact Evaluation since 2 years now. And one of the stuff I had to evaluate was less than 400 lines of code of Python and 400 megabytes of training data. So that was quite small, but the image was more than 20 gigs. So it was super long and super slow to download, and then it's not really necessary at this point. And especially if we consider this not in terms of research, but in terms of teaching. When you're teaching, you're in constrained environment. It could be a tutorial in a conference and you're relying on the Wi-Fi of the conference, or it can be in the lab with weird edu-roam setup or things like this. And then you have suddenly all the students that need to download 1 gig. Can be a nightmare. It can really ruin a session. So really need to take care of the size, also prepare, and you can ask people to prepare things by pulling the images, not really executing, but you can at least ask them to pull the image on their computer so that they have it and it minimize the bandwidth. Something which is quite common is to use Alpine Linux instead of Ubuntu, because Alpine is a very small, that I think it's the smallest version of Linux that is available quite easily. But then when I was bundling the MDE in the IoT context learning resources, I've tried for 2 weeks to have the Arduino plus Java plus Lustre plus Visual Code working on Alpine, and in the end I gave up and I went back to Ubuntu because there was like weird shared library issues that were preventing to deploy the stack. So that's also something which is part of the lessons learned of this. As you're basically describing in the Docker file, the command that needs to be executed inside your image, you're basically a system administrator. So you need to have the knowledge about how to install those things and how to package those things. It's quite easy 95% of the time, like as we done it together today. It took us like 25 minutes to have something up and running, but the 5% that is not covered by the easy pass, and it can become a nightmare. And something which is also quite annoying in Docker is the caching semantics. We've seen during the demo that Docker caches intermediate results because it's work on this layer model, which is also compositional. So each instruction is what Docker called a layer, and then you're building your image by composing layers together on top of each other. And if you haven't touched a layer, then the layer is not recomputed, which saves time and saves bandwidth. You remember when we pushed again the image, only the last layers were pushed, and the first one, which contained the operating system, wasn't pushed to the hub. So that saves time, which is quite cool. But it can basically make your life a nightmare, because you look at this, like at day 0, you're running an update of the package system, and then you're installing X. So basically X is installed with the latest version available. And then a year after, you're running, you also have this instruction, but it's not touched. So for Docker, it's untouched, so no need to recompute. So basically, even if part of the Docker file, it will not be executed. So this will not be updated. And then this one was changed because now you're installing Y and Z. So X, Y, and Z will be installed with the updates that was done a year ago. So it means that in a way, your builds are time dependent based on the caching mechanism. There's ways to invalidate this and always say like no cache, don't use the cache, but then you're computing and computing and computing again and again over things, and it's also your responsibility to do this. So you can have like really tricky and nasty bugs just because of the caching semantics in Docker. So to conclude, containers are incredibly helpful, really helpful, and Docker makes it kind of easy to define very simple containers. There's also a lot of documentation available on top of Docker. So the documentation is quite comprehensive. You have what is called the Docker Birthday, which is each year they're providing a new tutorial about how to, like it's Docker 101. So you just follow the steps and it works. In 1 hour, you have a web application up and running and containerized. So that's kind of really cool. But really, after a couple of like 7 years working with this stuff, use with caution. It can really trigger subtle bugs and issues, and also the image size could be quite a problem. We can have some discussions, but first, I just would like to use this as a blatant advertisement. We are seeking for a lot of PhD students and postdoc position with Richard at Mac. So if you do have any people working in the MDE community who wants to discover the joy of winter in Canada and summer in Canada, just really feel free to shoot us an email, because that would be really appreciated. And that will be all for me. I actually wanted to make it a little bit shorter, but that's good. And we can use the remaining time to just like have a discussion, or like basically we can also stop the session here or go through the questions that were asked in the chat.